My name is Jinzhou Shen from Florida International University. Today I'm going to present our paper in CVPR, a geometric algebra-informed 3D Gaussian splatting framework for wireless scene representations. I'm going to talk about our paper in two different sections, the framework and our experiment setup and result. So firstly, our goal is to reconstruct wireless signal fields from spot measurement, including RSS prediction and spatial spectrum reconstructions. The main challenge is that the indoor wireless propagation is highly complex. Signals are reflected, diffracted, transmitted, and attenuated by walls, obstacles, and other objects. Existing data-driven 3D Gaussian-based methods can represent wireless field efficiently, but they usually do not explicitly model ray-object interactions. Therefore, the core contribution of our paper is to introduce geometric algebra into 3D Gaussian splatting so that the learned Gaussian representation becomes more interactions aware and physically meaningful. Besides, we have our self-collected dataset. The first important component is the scene mapping network. It takes 3D Gaussian primitives, transmitter information, and scene-dependent wireless measurement as input. Instead of using Gaussians only as geometry primitives, our method attaches wireless-related attributes to each Gaussian, which relate to attenuation and signal-related features and geometric-aware latent representations. Another important design is the residue Gaussian adaptation. So our network produces residue updates for each Gaussian parameter, including rotation, scale, attenuation, and signal attributes, which allows the Gaussian primitives to adapt wireless propagation structures. The second key component is the GA-informed multi-view tokenizer. Directly applying attention to all Gaussians will be computationally expensive and may include many less relevant primitives. Therefore, our tokenizer selects the top opacity Gaussians as anchor scatters. These anchors usually correspond to important propagation structures such as walls, obstacles, and all other strong reflecting regions. Our tokenizer is also transmitter conditions, which is important because wireless propagation depends strongly on transmitter location. By combining Gaussian features with the information, the tokenizer can model transmitter-dependent C responses. Finally, the tokens aggregate the multi-view interaction information and provides global propagation context to attenuation and signal branches. Next, the main technical contribution is the geometric algebra-informed interaction modeling. In this formulation, the wireless ray state is represented as V, and the interaction with the environment is represented as an operator I. The transformed ray state is written as V primes equals I V I inverse. This sandwich product form provides a unified way to describe different propagation interactions. For example, reflection can be represented by a reflection-related operator. Diffraction-like bending can be represented by a diffraction operator, and etc. This design is useful because real indoor environments usually do not have accurate material labels or exact ray collection annotations. Instead of explicitly tracing every ray and every interaction point, our method learns this interaction effect implicitly through the geometric algebra-informed token representations. As a result, our model adds a physical inductive bias to 3D Gaussian spreading, making the representation more suitable for wireless channel modeling. And next, I'm going to talk about our experimental setup and some results. Our experiments are conducted on both self-collected and public dataset. For our self-collected dataset, we collect indoor RSS measurement in two rooms, referred to as Room 1 and Room 2. The measurement cover both 2.4 GHz and 5 GHz Wi-Fi band. Our hardware platform includes a Turboboard 4, a Raspberry 4, and a Wi-Fi adapter which enables specially referred RSS collections. We also evaluate on public ISA and RFID spatial spectrum dataset. And we have so many baseline to compare with. And the next slide is the 2D spectrum visualization, the performance compression, CDF SSF curves, and I'll predict ISS heat map. And thank you for your listening. If you have any questions, please email to the following email address. Thank you so much.